Okay, so welcome to the new session of this summer internship in Computational Nuclear Astrophysics 2025. Today we are gonna discuss, we will be continuing our discussion about Walecka model, right? And as I was discussing, I have updated this PDF. I put some additional information and I made it more smooth so that you guys can relate. So I can quickly go through that changes and maybe revisit some of the complex things, right? So this is the table of content. Okay, we already went through that. What is the idea, what is the motivation behind Walecka model or any mean field model that is based upon one boson exchange. Okay, we did that thing. And then we talked about what is the motivation for infinite nuclear matter, like this is an assumption so that we can solve our equations easily. And nuclear saturation properties, these are very important, that are experimentally obtainable, and when you have something experimentally obtainable you can fix your model to that, like you can calibrate your model and you can fit your model to that properties and you can extrapolate to certain densities where experiments are not reachable. So this is the idea. So I talked about like various saturation properties, okay, which are very important, and for any model we have to check that, right? And then we talked about Lagrangian density of Walecka model. The particles we were interested was like how, for example, neutron interact with the exchange of sigma and omega, right? And sigma was for attraction and omega was for repulsion. So this is the simplest model. We can have many mean fields, but right now we just go with sigma and omega. So what matter we are interested in? We are interested in nuclear matter. When I say nuclear matter, only neutron and protons are degrees of freedom there. Okay, so you have to take that in your mind, and that's why the psi field, whenever I talk about psi field represent the fermionic field. In this case, this is just proton and neutron. Okay, and then we have like whatever degrees of freedom, whatever the particles are involved in our system, we are gonna construct the Lagrangian density out of it and their interaction. This is the idea. And scalar meson term we discuss about Klein-Gordon Lagrangian, and we discuss about vector meson term, we discuss about electromagnetic Lagrangian, not exactly electromagnetic because we have a mass, but vector Lagrangian for vector mesons. Then we have interaction terms where we discuss, okay, we showed by a rough diagram that sigma omega interacts is the force carrier that basically make that interaction happens between n and n, neutron and neutron. But how can we write mathematically? We can write mathematically like psi particles antiparticle of nucleon or fermion interacting through psi sigma, right? And there should be a coupling between them which defines strength, like how strongly they are coupled to sigma. And similarly this thing is here. Why there are gamma mu here but not here? That is a separate theory, separate talk. Like we can discuss about Dirac bilinears, how scalar goes, how pseudoscalar goes. So if this is a scalar field, obviously, sorry, not this one is a scalar field, this one is a vector field, and the Lagrangian is itself a scalar field, right? So to make this scalar to make this vector a scalar, we have to multiply it with something. We have to contract the indices. That's why gamma mu is up, omega mu is down. One is contra, one is co. So that's why you have a scalar at the end. Okay, so and then we have the total Lagrangian, which is the same for all those things. So this document is more or less the same, but now a bit organized. Then we have Euler-Lagrange equation. Why we need that? I discussed with you that I want to get the equation of motion for the different degrees of freedom and particles involved. So I started with the equation of motion for the nucleonic field, which is this, and dl by sigma. I did all this thing, you know, I put some mathematical steps so that you can relate. So you go through that, and let me tell you, this has not been proofread. Okay, so if you guys find any mistakes, do let me know. Maybe I'm missing some 2's or something, do let me know. So I need a person who can proofread it. So do tell me, and these are the steps like how to get the equation of motion of scalar field sigma. Okay, similarly we can have that for vector field. So I did that. So we get something like this box operator. Box is nothing but mu d mu. Okay, this is a fancy D'Alembert operator here. And then we have equation of motion of vector field as I discussed. So this is the equation we get at the end. Now again I am just going to emphasize one fact that, see, whenever the derivatives are involved, right, like these things, it is very hard to solve such equations. It is not easy. There should be many assumptions, there should be many boundary condition in that case. So we want to simplify our system. And now, you know, we are a scientist, we love symmetry. Whenever we love symmetry, like we always, not whenever we love symmetry, if we love symmetry, so the symmetry tells us to find some symmetrical things, some constant around it. So when we are interested in symmetry, it gives us some invariance. So when we see invariance, we get a conservation law. So conservation laws makes our life very simple, very simple. So if we don't have a conservation law, it will be very difficult for us to construct physics, right? We have to find meaning in every small detail. So can you guys tell me what theorem links symmetry to conservation law? Can you speak? Are you familiar with any theorem that links symmetry with conservation laws? No? Okay, Noether's theorem. Amy Noether was a lady, like great mathematician, who developed that. Okay, so it basically relates conservation laws to symmetry. Anyhow, so we were talking about mean field approximation here. So mean field approximation is like, initially our sigma was dependent upon x and t, omega mu was dependent upon x and t, but we said that there is a translational invariance in the grid. Okay, so we don't have like different values of sigmas here and here, but we are assuming that they are same everywhere. So this is a relaxation which can work in this case, but it doesn't work in some of the cases when temperatures are very high. So we are gonna not discuss about that, but for a start we can go with the mean field approximation, and in that meson fields are approximated by their expectation values, quantum fluctuations are neglected, only time like component of the vector field survive due to rotational symmetry, all those things. I am not gonna emphasize about it more. So if you are interested, you can go, where did I put a reference? Maybe one. Yeah, I can just show it here. Come on, this document is too big. Yeah, you can go to the first reference. I have discussed the mean field approximation very clearly, very carefully there. Okay, so you guys can discuss. Now we have mean field approximation, detailed derivation. So what I told you, so x is a 4 momentum thing, right? It is not just x like 3 x's, it is just, it is x0, x1, x2, x3. So you have to be careful about that. Now it has been changed to what? A mean field, like sigma bar is nothing but an average. So similarly this. Now we have one equation of motion for nucleons, which is this, and we get an effective mass. We can identify the effective mass like this, and these are the interactions. And since there is a rotational symmetry, so we discussed in the previous here that only time like component of the vector field survive due to rotational symmetry. So due to rotational symmetry, only time like component will survive. Like omega mu, we have omega 0, omega 1, omega 2, omega 3, but omega 1 to 3 will go away because of rotational symmetry, they will not contribute. That's why only omega 0 will there. So that's why it only survives, or you can say it doesn't have any source. So meson field equations, what we get, like we have now these derivatives, right? We have these derivative as well as these derivatives. Where is that? The box, and box is nothing but d mu of sigma. Now since sigma doesn't depend upon space, or it doesn't depend upon time, the derivative makes no sense, right? So it basically becomes 0. That's why we get the equation of motions like that. So these are the two equations of motion which are very important, like which will we will build our code on top of that. And then there comes a question, what are ns and nb, how did we identify it? Okay, so ns and nb are nothing but these psi bar. So whenever you do some, so you can see here, so there are psi bar psi, right, psi bar psi, and there should be a psi bar psi here as well. So what we do, we identify ns as psi bar psi, which is psi dagger gamma 0 psi, okay, and which expression comes like that, where gamma is the degeneracy factor, and for fermions it is 4, 2 for spin, 2 for isospin, okay. And similarly baryon number density is nb, which is psi dagger psi, and the expression is like that, and it goes like that. So I am talking about 0 temperature here, okay. So we have like ns and nb. For 0 temperature case I have written these things here. So this is so as I told you yesterday, like whenever we have a system at t is equal to 0, how do we define Fermi level? It is the highermost shell that has been occupied, right, at t is equal to 0. So that we know the momentum goes from 0 to the highest filled shell. So kf, that's why it goes from 0 to kf. So I'm not going to talk about the plane wave solution, it has a lot to say, I'm not going to overwhelm you, but you have to believe me that ns is defined like this, nb is defined like this, and then we have a chemical potential, which the effective chemical potential can be linked to the normal chemical potential, and these are the corrections. So what do I mean by chemical potential, effective chemical potentials here, or effective mass? So there is a difference between two notations, one is m star, one is m. So m star is the mass when the particles interact with medium, how does it change its properties, for example mass, it is denoted by star. Similarly mu star is also when it interacts with medium, what is the medium? Medium is interacting through the mean field mesons. So when it is interacting through the medium and it is giving some corrections to mu b, then it gets modified and we call it mu star. Okay, similarly for m star. Now we have this expression for scalar density here, okay. So we have this expression for scalar density, and this is for vector density or baryon number density. It is quite simple, you can do this integration and you get this, okay, it is simple. But this guy is a bit complex, you have to solve it, right, and when you solve it you get something like this analytically, okay. So this is a definite integral 0 to kf, when you solve it you get something like this. So if you find some time, maybe you can do this exercise from line 30 to 31, very simple trigonometric integral exercise you have done, like plenty of them in your +2 level, okay, or BSc level. So you can do that. But one thing I want to say is, when we talk about a distribution function, for example, okay, I have not shown distribution function here. So the definition of NB is, for example, NB is in general gamma upon 2 pi cube 0 to infinity d cube k, and then there is a distribution function like f of k plus f of k, okay. One is antiparticle, one is particle. So for baryon densities is negative. So we have distribution function fk is equal to fk minus f bar k, okay. So this is the general definition here, and when we plot the distribution function, it has a curve like this, right, but when it is a 0 temperature it approaches to a step function like this. So when it approaches to a step function, so we define it as a step function denoted by theta, okay, and we modified our expressions for a 0 temperature limit, and we get this and we get this, okay. So kf is the Fermi momentum related to nb, gamma is the spin degeneracy factor. Now what is next? Can we calculate the equation of state? Yes, we can calculate. The total energy density can be written like this. So this is the standard definition, and these are the correction from mean field, like sigma correction and omega correction to energy density. And again you can solve it analytically, you get something like this. For these things you get something like this. Okay, similarly pressure is defined as this. Okay, and we have correction from mean field sigma, mean field omega, and we get something like this. So these are the relation that you have to remember. Okay, so if you want to learn more how I have written it, then you have to dig deeper. Again I would say reference number 1. This paper is very comprehensive and we have discussed everything, like how we get each expressions. But this will not exactly match with CMF because our paper is chiral mean field model, but at least it can give you some insight, like how we start with all those things, how we calculate total energy density and pressure from the energy momentum tensor. Okay, so if I will talk to you about all those things, then it will be like a PhD coursework, so that's beyond this internship. Okay, so you can always refer to the reference 1. So we discuss merit and demerits, let's not discuss that. So I also wanted to talk about application to neutron star matter. We will do that after our code. Okay, so let's go to the flow chart and try to understand our problem. Okay, so so before that, let me give you some motivation about what we are trying to do here. So these are the observables. Are you guys with me? I'm not able to see you. Can someone just say hi? Yes. Okay, thanks. Great. So see, these are the observables. Observables, like I can calculate this after. I don't need to worry about this right now. So if I have the information about sigma, I have information about omega, and sigma and omega are constant, I can just give it to my code from outside. If I have some information about sigma, omega, and then I have information about effective mass or kf, then I can calculate this quantity, which is not a big deal. So I don't have to solve my system of equations simultaneously in order to calculate total energy density and pressure. Same goes for that. So what my main goal is, I want to understand, since my observable is based upon sigma, omega, like the fields, so I want to calculate this thing here, like how sigma and omega varies with either NB or mu b, how it behaves with the baryonic density or baryon chemical potential, right? This is our goal. So in order to do that, we have to think like what are the equations that we can solve. So we have two equations of motions, okay, EOM. So we have two equations of motion, one is with sigma and one is with omega. So when we solve these two equations, these are not coupled. These are not coupled yet. When it will be coupled, if I have something like that. So we have like cross things. Then it is called a couple system. But right now it is not a couple system because we are working with the simplest model. Okay. But these are two equations and they are non-linear. Are they non-linear? They are not non-linear. They are linear. Again, this is the simplest one. So we need to, but they are interdependent in some case, because in NS and NB we have a common factor which is K. Okay, this guy K. We have this common factor. So we need to solve these two equations simultaneously in order to get something. So we have two different equation and we want to solve it simultaneously. And these are linear equation, non-coupled. How can we do that? We have to rely upon some methods, some numerical methods which are able to do that. And we will go with, you can do Newton-Raphson method, but I will go with fsolve method, which is an inbuilt function in Python. Okay, which is to solve non-linear coupled equation. Okay, so but here the system is linear simultaneous, non-coupled. So this is the simplest case I am talking about. So I can show you a couple complex system later on when we are done with this particular thing, right? So our end goal is, so I am repeating myself again, our end goal is to solve this system of equations and get the value of sigma and omega with respect to mu b. Okay. Now the next question that might comes to mind, like how can I vary mu b? How can I vary nb? Is there a way? Yes, there is a way. So we can do that. So how can we do that? We know that like mu star at 0 temperature, mu star is nothing but k square f plus m star square. So this is the definition. From that definition I can calculate my kf as mu star square minus m star square, something like that. Okay. So if I give mu star I as an input to my code, it will give me the corresponding kf and m star square. Okay. And for each mu star, like if I am looping over mu b, this is mu b, if I am looping over mu b, it will give me particular kf at every mu b, and that particular k will go here in the densities. Okay, and the densities, and then it will go here, and for a particular mu b, the system of equation will try to solve itself, like the solutions which fits both of the equation, and if fits, it gives the output and we store that solution. Okay. And what is m star? M star is nothing but some function of sigma. Okay, mn minus g sigma sigma. So this is the rough idea that what we are gonna do. So let's execute it more clearly. Let's talk about a full flow chart. Okay, so we need to construct, whenever we are writing a program, computer program, it is always helpful to start with the flow chart. So what is our idea, what I am gonna do? So first of all we start, and again what we do, we define some model parameters, like we can check, okay, there are some constant which are gonna constant throughout the code. I will just write, okay, I have m sigma, I have m omega, I have some sort of parameters which will be constants, right? So I just put it there in this particular block, and then I will think about, like, okay, how am I gonna play with my code, what parameters I want it to iterate with, right? So in the parameter, the variable I want it to be iterated with is chemical potential. So I want something omega with respect to chemical potential, so it changes with chemical potential, it gives me some value. Okay, so I input a baryon chemical potential, I put a layer here, and then I just don't want one chemical potential, I want multiple chemical potentials. So if I have one chemical potential, it will go like this, yes. If yes, then it will go for, so it will first calculate the Fermi momentum function. As I told you, it will go look for kf and it will try to calculate this thing here. Okay, for each mu b it will give a kf, and I get that kf, and this is simultaneous, so it should not matter. So for kf it goes to calculate the effective mass. Okay, and the next problem we have in our mind is m minus g sigma sigma. So it will calculate the effective mass and so store it here. Then the next thing it will go is the scalar density. It will try to compute a scalar density, because scalar density is a function of kf and m effective mass. So we have to understand that whatever the arguments we are providing for the next function should already be covered in the previous function, right? So kf we have calculated in this, m effective we have calculated in this, and scalar density we will calculate using these two things, and the vector density also, it only depends upon kf, so it is fine, you can compute it here, you can also compute it here, doesn't matter. So then we have compute meson fields. So since our ingredients are ready, like we have so our main equation, if you remember, we only have variables like ns and nb. If we have ns and nb ready, we can solve our simultaneous equation, which is this part. Okay, and then if we are done with it, we can calculate the, when we have the solution, we can calculate energy density, we can calculate pressure. Okay, and we store result. Now for the next loop it will go again. If I want more next mu b value, I am iterating over mu b value, it is gonna repeat the same thing again and again until I get the last point within the mu b value, and if it, when it is no, it will just plot the quantities. Okay, so I am not gonna do that, so it will plot the quantities. So this is the central idea what we want to do. So now let me, okay, before switching I am gonna wait for 1 minute so that if you guys have any questions. Okay, you don't have any question, then I will just switch to my PC. Okay, very well. Now let's switch to the code. See, we are gonna touch base again, like I'm gonna repeat this again and again because I want you to understand this pretty well, right? So as I told you, the code blocks within the flow chart, we start with defining the model parameters, some constant or model parameters. So I need to identify something. What I am going to identify first is, okay, I put, so this is a Jupyter notebook. You can either work in Jupyter notebook or you can also work in a single Python 5, normal, simple. So let us start with simple constants, physical constant, and which is, I defined a variable h bar c, and which is 197.327. Okay, so what does that mean is, if I wanted to convert, see, I will be working in the some units, like some unit system, like let us say SI unit system, whenever we do a normal problems. But when we do talk about particle physics, we mostly prefer natural units. So what is natural unit? Where we can take h cut and c as 1 and we can modify our other units accordingly. Okay, so whenever I wanted to, using this relation, whenever I wanted to convert Fermi to MEV and MEV to Fermi, I will use that expression. Okay, so I am gonna do that. Let me actually show you how. So see, in natural units we have something like 197 point, was it 327, right? Where was I? Yeah, it is 32 MeV Fermi. Okay, this is the standard relation in natural units. Not in natural unit, but standard relation. Okay, so this is a standard relation. Now what I want to do is, in natural units what I will do, h cut is 1, c is 1, so it will be just 197.32 MeV Fermi. Okay, so I can calculate what is my MeV, which would be 1 upon 197.32 Fermi inverse. So we have this relation now, right? So I can convert my MeV to Fermi and Fermi to back to MEV. So it depends upon whether I am dividing this guy or multiplying this guy. So I just declared a variable for that, h bar underscore c. Okay, so I declared a variable and I will use it as per my need. Then I am using pi's again and again. One way is I can define pi is equal to 3.14. Another way is I can simply use numpy and just get pi from numpy. Okay, that's why I have imported numpy and defined pi as np dot pi. Now what are the model parameters? So whenever we talk about a model obviously it has a parameters like by which we can tweak the model and fit into something. We can fit into some mathematical constraints, some experimental constraints, right. So here I have put two parameterization. One is TM1 parameterization, which is of the Walecka model itself, like very well tested, and the parameterization is this, and this parameterization is fixed to calibrated to get the binding energy within the constraint and compressibility within the constraint. Okay, so these are just here to show, there is no need of for this code to go through that. That's why it is commented. And then we have the parameters like what is the vacuum mass, degenerate vacuum mass, nucleon mass in MeV, and then we have m sigma, mass of sigma meson, mass of omega meson, we have couplings g sigma, g omega, and then we have a saturation density defined, which we gonna use later. Okay, and then we have gamma. Gamma is nothing but the degeneracy, 2 for spin, 2 for isospin. You know, for each fermion there is 2 spin, half and minus half, and for each strong interacting particle like nucleonic system we have protons and neutrons. So protons and neutrons are isospin degenerate. If they are isospin degenerate, so we have to multiply by 2, so that we count them as 2, not 1. So that's why the total degeneracy is 2 multiply by 2, 4. Okay, and then else, in the else command I have a custom constant parameters, right, which I have taken. I have varied my m sigma a bit, right. It doesn't have a strong constraint over from PDG itself, so therefore I have changed it a bit so that I get something. I am having some problem in the code. I will explain why this happened. Okay, so so this is the custom set I am gonna use. And when we say PDG, particle data group, I hope you are familiar with. Particle data group table lists all the particles and it shows the latest constraint over it, like what is the mass of pions, what is the uncertainty band around it, all those things. So m sigma is has a wide range. This particle is not much studied yet due to some constraint, I don't know. And also I have put here the reference for the paper where this parameterization has been taken. Okay, so far so good. We have model parameters defined. Throughout the equation I identified which are my variables, which are my model parameters, which are my constants, right. I understood everything and I put it down in my beginning of the Python code. Okay, when I do that, the next thing that comes to my mind is I want to loop over chemical potential, right, because the end goal of my thing is I want sigma versus mu b, and if I am looping over mu b, I need to communicate my code like, okay, it understands and it finds a connection within mu b. So how can I do that? I can do that using, let me just, I just want things to be perfect. So mu b, so I am looping over mu b, but whenever I am giving mu b as an input, it should calculate what? Kf, the Fermi momentum, which is the outer part of the Fermi shell, right. So we have mu b star square minus m star square, as I told you, this is how we define it at 0 temperature, right. And I defined the Fermi. Now I guess you guys can relate the functions itself, like how does all these things go. You guys are, I think, well trained now. So we define a Fermi momentum function in Python, and the arguments it is taking is obviously mu b, okay, and effective mass, okay, and within the effective mass, you know, there is within the effective chemical potential we have omega dependency, right. So that's why we need to put omega here as well. So what we are gonna do here, the Fermi momentum expression is mu star b square minus m star square. So I'm gonna return this value to the Fermi momentum function itself, okay, so that it stores the value of Kf. Now what are the input variables I want? Obviously, see, again I am telling, in mu star b, what we have, mu star b is nothing but this mu b minus this guy and this guy, right, which is very simple. I can write it here as well. So mu star b will be what? Mu b minus this guy, or this guy minus g omega omega something. So you can do that. So this is the expression I have written here. So for the function itself, I need three variables, mu b, effective mass and omega, so that I can use that. And g omega is constant, I do not have to provide its value, it is constant throughout. And there is one important check I wanted to give is, you can see from this relation here, if mu star b is less than m star, what will happen? The kf will become imaginary. When kf is imaginary, the error will propagate through the code and it might disturb the next iteration. So I do not want to do that. So what I am saying, my code is, if you detect that the effective chemical potential is less than or equal to m effective, which is the case, it avoids it to become negative. Okay. Imaginary. Okay, and then it prints that, okay, for this mu b this thing is happening, and in that case return in this function that it is 0. Okay, return that mu effective is 0. Now in this again, what have we are returning in totality in this function, this kf. Now this, we have this function ready. So we right now we don't need to pass any input, we just made a function, right? So we can use that later. Now the next thing that comes to my mind is, I have kf. Okay, what I can do with it? I can calculate the scalar density out of it, and the expression for scalar density is given by this. I took it from my notes. Okay, and the scalar density depends upon two things, as you can see this through this. It depends upon the Fermi momentum variable and effective mass variable. Fermi momentum we have already calculated in this part of the code, and effective mass is this, defined as this, Gn minus G sigma sigma. G sigma and Mn is constant, vacuum mass of nucleon, G sigma is the coupling strength of sigma, and sigma is a variable which we are trying to solve simultaneously, which we try to fit. So scalar density, how do we do that? Two arguments, very simple. What we are returning? We are returning this whole thing. So how can we do that? We can break this as a term 1 and then term 2 and term 3. If we do that, we can return term 1 multiplied by term 2 minus term 3. Okay, I do not want to discuss all those things, but this is quite obvious. So you guys can relate my LaTeX PDF with this. I might have done some mistake. I have checked it, but still. Okay, next. I want to calculate baryonic density, which is quite simple. If I have Fermi momentum, I can simply get that. So I am just returning my expression for baryonic density. Now the real part of this code comes into picture, where I actually have to define my field equations or equation of motion. Okay. So I have to define my equation of motion. So I have two equations of motion, one for sigma, another for omega. I am gonna repeat again. This is non-linear, non-coupled. Sorry, this is linear, non-coupled, simultaneous equation to solve. So what there is a coupling, not in sigma and omega, but there is a coupling between kf, because ns has kf dependency and nb has kf dependency. So we have kf here, so we have kf here. So it is a coupled equation. So what we want to do is, we want to solve this equation simultaneously, like whenever we are changing our mu b. Okay, whenever we are changing our mu b, it is changing kf, the kf is changing ns, the ns is changing ns and nb simultaneously. But there are numerous solutions that it can fit, but I want that particular solution which fits through the both of the equations simultaneously. So this is my end goal, and for this I have to rely on some methods. Okay. So like bisection method, secant method, Newton-Raphson method, Newton method, all those things. So let us define our field equations. So how I am gonna do that? First of all, I have two variables here, x and mu b. Mu b is the input, x is the solution that I am gonna get after solving the equation. So let us put sigma and omega into a new variable x, and then already defined effective mass of nucleon in terms of vacuum mass and g sigma sigma, which is quite obvious. Now I called my function. Okay, I am telling my function that Fermi momentum, like I am giving you mu b, I am giving you m effective, I am giving you omega. For that, give me kf. This is how you use function. Okay, you are transferring the value. The function has already have a return thing, and return is passed through this variable. Similarly, I called for baryonic density function and I called for scalar density function. So I got these three things. Now time to define the equations. So the first equation is sigma g sigma m square sigma ns, which is this. Okay, I can write it in a fancy way, like you can see g sigma minus g sigma, which is sigma, like you just put this thing here minus this equal to 0. So this is how you write it in your code. Like equation 1 is this thing, and make sure everything on the right hand side is 0. So we just wrote it like this. Okay, and similarly for equation 2 we wrote it like omega 0 minus g omega divided by m square omega multiplied by nb equal to 0, which can be covered in equation 2 equal to 0. So we just defined two equations of motion here and we returned it. Like for this function, whenever I call this function, return me two values, equation 1 and equation 2, and in these equations look for the things to solve, for example ns, nb and all those things. Okay, so these are the field equations. Now this is the time to solve the equation of motion. So far we have just defined the definitions, right? We are defining some functions. Now we are gonna use them extensively. So we defined a function, we get that all this thing. Now when we go to the next thing, which is very very important, we have equation 1, we have equation 2. Now this time I want to solve that equation simultaneously. So what I am trying to do is here, let us go through this. So I defined a function, solve Walecka, and the only variable is mu b. Okay, and since I am gonna use f solve, this line, I am importing it from scipy.optimize library. Okay, so I am importing an option from this library. So this is a scipy thing, which is like symbolic pi, that is sympy, not science pi. This is science pi. Okay, we import a function f solve. So what f solve will do is, I am giving field equation function as an argument to f solve, that so that it understand what equation it has to solve, what equation it has to return. So I put it here, f field equations. So we can focus on either this or this. Let us focus on this because we are working on false case of true parameterization, if you remember. Okay, so false case, that's why we are working on this thing, and we are working on this guy here. Okay, now field equation is this, and then we have a box for initial guess, like how many f solve variables we have. We have two variables. How do we know that? From this. Okay, so how many unknown x's are there? Sigma and omega. So two variables, therefore we are giving two initial guesses. And what are the arguments? What we are iterating it over? Mu b. This is how you define a f solve, okay, in one line, and whatever solution it is getting by solving the f solve, just store it here, solve. So this is a tuple or list. Sol 0 is sigma, sol 1 is omega, or x 0 is sigma, x 1 is omega. Now up to this, what this function is trying to do, we are just defining it. So far we have just defined it. So what we get is we say our code that whatever solution I am getting, just put it into sigma and omega, right, line by line, and then calculate the effective mass of the nucleon. Now, whatever is the final solution I am getting, okay, before that it is just the guess we are trying. Okay, it is the guess we are trying, it is solving through the guess. But whenever the solution is achieved, give me the real M effective of nucleon, okay, and give me the real Fermi momentum, so that I can calculate my baryonic density. Okay, and what I want you to return, my code to return, like whatever is happening in this code section, mu b is the thing which I am wearing from outside. I will tell you in the next code snippet. And give me kf, give me nb, give me sigma, give me M effective, give me omega omega. Okay, so what I am doing here is, whenever this function has been executed, give me all this value, like whatever is in mu b, just return it to this string and all those things, right, one by one. Now how do I run solver? So far I have constructed the function. Now this is the time where I am going to execute my code in this code snippet. So how am I going to do that? First of all, I will define a list where I am going to iterate it over. Like what I am doing is, I have defined a list where mu b values I am interested in. I am interested in starting from 922 to 1601, okay, and with the step size 1. So I want to change my chemical potential from 922 to 1601 with the step size 1, okay, and I want my solver to go through each mu b value one by one and give me a solution, right. So this is what this line is telling me, that solve this function with this argument, okay, and for loop is over this argument again, and how it is fetching the values, it is fetching the values from this array, this numpy list, okay. So m mu b value here, so for each mu b, let us say 922, it gives me some solution, it runs through all the parts. So for example, let us go through that. So I gave 922 went here, 922, the for loop picks 922 and it put it here, and this 922 will go here 922, and it will go through the whole code, that okay, for mu b 922 these are the initial conditions, okay, start with initial guess is 20 and 10 for sigma and omega, and you go through the equations, okay. When you go through the equation, you put sigma and omega, like sigma and omega as 20 10, okay, and you put everything here and you try to solve everything here, because we just need sigma and omega, everything will be calculated in terms of sigma and omega. So M effective mass will be calculated in terms of sigma, NB is Kf, which we calculated from the mu b itself. So this is a chain of event which happens when we do mu b, and using the functions, we are calling the function wherever we need them. So when we do that, it gives us a solution for 922 and it stores it somewhere, okay, it stores it. But now my next question is, like, I just don't want one values, like I want to store all the values in a column. How do I do it? For example, I extracted NB from this particular section, but this NB is showing me result for only one iteration, just one mu b, but I want to save it for the whole mu b range. How do I do it? I have to create a list, obviously. So how I will do? I will declare a new variable I will declare a new column. Okay. So in list res list for res in results, like we have results here, where is that? So results contain all the information which loops over mu b. For each mu b, give me this guy. Okay. So for each mu b, the function is solve Walecka, give me this guy. So for each mu b, it is extracting and it is saving it here. And why I am dividing it by h bar cube c cube 3? Because I want my density to be printed in terms of Fermi inverse, not MeV inverse, MeV cube, because my whole code is in MeV, but density is some quantity which I want to look in volume, in terms of volume. So I am changing the units later on, that is why I am dividing it by h bar underscore cube to power 3. Now I want to extract the effective mass, same thing, you know, sigma, same thing. This is just like I am putting it, collecting the information piece by piece, and I am putting it all together in a list. So this is just that, so that I can plot. Now first of all, I will run it again, the whole thing. Okay. So I run it all together. So now I am gonna plot it, whatever I have done so far. So these are the plotting script, you are well you know everything about it. So what we observed, that mean field sigma and omega, like here, versus NB, and I have divided by n sat. Where is that? I have not divided by n sat, but I am showing it here. Okay, I have divided it here. M effective wall. Okay, let me just copy this thing. We can do that easily. Am I printing with respect to, okay. If you remember, I defined this constant n sat at the very beginning in the column. So I will just copy it here. Okay. So if you remember this guy here, so I already defined that the n saturation density is 0.16 Fermi inverse cube. Okay, anyways, so I just converted this to NB by n sat, so that I can think in terms of 1, 2, 3, 4, 5. Otherwise it will be like 0.1, 0.6 and all those things. So I can say at saturation density, the value of sigma is it, value of omega is this. Okay. So yeah, so this is a very simple thing, like from the plot itself you can see the sigma is increasing and the omega is increasing linearly. So omega is showing, since omega contributes to pressure positively, if we have more omega growing, that means we have more repulsion, right? And you can see it from this thing here, omega contributes to the pressure positively and also energy density. So if we have more omega growing with respect to mu b, that means the equation of state will be more stiff. It is a direct observation. Okay, so we have observed this thing here, the mean field omega is growing like this and sigma is growing like this. So we have plotted this in terms of NB by n sat, baryonic density. As the baryonic density is growing, how mean fields are changing, and we can do the same plot with respect to baryon chemical potential, right? So we can do that. So which is this? So it is up to you in which you are interested. Then we have plot effective mass versus baryon density. Okay, again I am not gonna discuss all these things, so you guys are already familiar with that. So I plotted m star NB by n sat. What does that mean? Whenever the particle, the nucleon start interacting with medium, like the medium is growing, what is baryonic density? Baryonic density is like the number of nucleons in the system is growing from 10 to power 17 kilogram per meter cube to now 2 times 10 to power 17 kilogram per meter cube. I am talking in terms of kilogram per meter cube units because it is easier to understand, but let us switch to Fermi inverse cube. So, when I say 10 to power 17 kilogram per meter cube, I am saying 0.15 Fermi roughly, Fermi inverse cube. So, as the density of the medium increase, the effective mass of the nucleon decrease, and at saturation density it is around 550, let us say roughly. This is a Jupyter notebook, I will not be able to see the value. I have to execute this code in single Python script, then I can interact with my Python interactive window better. So, the effective mass, okay, M N So, the effective mass at saturation should be around 600 or 550 roughly. This is also a constraint. Okay. Actually, I remember a constraint. It should be around 0.65 mn. If your code is reproducing that, then it is good, like around that value. So, 0.65 would be, what is the 938 into 0.65, okay, 609. So, if it is giving us the saturation density, effective mass at saturation around this is good. Okay. So, for our parameterization, we got it around 550, okay, which is not bad. What else? So, we can plot effective mass versus baryonic chemical potential, which is fine. Now, the next thing that comes to our mind is, okay, what about the observables? So, the formula of the observable, the analytical solutions are written here. So, I want to implement that. So, I created a function for energy density and pressure. I put the values here. Again, how can I calculate? Let us find the variables here. So, we need Kf, we need EF, we need M star, we need sigma, we need omega, rest of them are constants, right. So, I have put everything here. Okay. So, I put everything here. Now, the next question that arises in our mind is, like, sigma is not just one value, it is a array. So, we have to pass array through this function, so that it has number at every point for mu b, and it adds up all the things, and it creates a new energy density list. Okay, we are just playing with data frames here, we are just playing with data. So, how do I do it? I created a function, I created two empty list, I created a function which loops over NB vals, and it calculates the Kf, and from that whatever I need in my energy density function, energy density expression, I calculated that, and from that I calculated something, kinetic energy and Meson energy, and I divided it by h bar underscore cube multiply 3. Why did I do that? I will tell you in a minute. But what I am doing, I created an empty list, I looped over all the variables, and when looped over all the variables, at the end I am appending each and every entry to the list. So, for each mu b, for each NB, I am appending this. So, I am making a huge list for each NB. Similarly, here for each NB. Now, why I divided by h bar c cube here? Because I want my energy density to be in terms of MEV underscore Fermi cube. So, right now the units of my code is MEV. So, it will show everything in MEV, MEV4 for example, for energy density, but I want to show it in terms of MEV Fermi cube, which is more suitable units when we are comparing the equation of state. Okay. So, you can relate, like it goes from around 0 to 1000. So, it is easier to see. If we do MEV4, it will be a crazy number here. So, it is better to deal with the MeV Fermi inverse cube. Now we plotted energy density versus baryon chemical potential, which we saw something like that, and there are some outliers, I guess, maybe one or two. And then we have pressure versus baryon chemical potential, right? And then we have pressure versus energy density, which is our equation of state. So we are interested in this plot, pressure versus energy density. Like, see, you can see this, okay, and from that you can see the pressure, as the energy density is increasing, the pressure is increasing, and which tells us that equation of state is becoming stiff. How do we know equation of state is becoming stiff? If the equation of state is leaning towards the pressure, then it is becoming stiff. If it is leaning towards the energy density, it is becoming soft. So if we have more stiff equation of state, then a star can support a large mass, like the particles are packed, that's why they have more pressure, repulsive. So from the pressure itself, by looking at it, we can see how the star can support mass or not. If the pressure is stiff, the star can. If it is soft, the star will not. Okay, so this is a very important observation, that pressure, how pressure is changing with energy density. So you can see. So at the end, I'm gonna talk about, like, okay, I want to reuse this data file into something. I want to use that equation of state in my TOV solver, in my Tolman-Oppenheimer-Volkoff solver, which gives me the mass radius. For that, I have to transfer this to the some text file. Okay, so we already discussed it. This is how we transfer it. We define the columns, we relate it to the particular list, okay, and then we made it a data frame, and then using the .to_CSV function of pandas, we basically created a file, Walecka output eos.txt. So we can just open it, this one here. So I have this data file here now, okay, which has been generated throughout. So far I have not shown you this because we were working in the we were never showing it, we were just working in the plots. So this is how we construct equation of motion code like Walecka model, which is the simplest one, and this is how much lines are there, 777, come on, no, it is something else. So this line is this code is around 200 lines, I guess, not more than that. And you can also compact it, you know, these functions are using, I am using this again and again. You can create a new function, you can just put one line there. So you can think about like how you can minimize this code, but right now the goal should not be optimization, it should be about learning physics, even if you are writing a big extensive code. So it is not about you focus on optimization, you focus on just learning, like how can I understand this code. At last I want to say few more things. I'm going to go with the discussion session after this. See, this code is not 100% physical, okay. I am using some values which are not properly fitted. So this code is for demonstration, to tell you things like how things works, how a mean field code works, how you calculate the equation of state from something, okay. So this so you have to keep that in mind, this is not 100% physical results. There are some complications. For example, let me tell you this thing here. I think the pressure is negative here. A pressure cannot be negative, right? If it is negative, it is a metastable state. So we are not going to discuss about that, but there is one observation here. And also, if there are some outliers, if the curve is not continuous, maybe some point is going here and there, maybe some infinities are there in the code, then it is also not good, okay. So this is the outlier, I feel like. So there are some fluctuation, there always be, this is research, right? You are going to play with your code and see where you can improve. Also, one important thing is, it also depend upon the step size as well as the initial guess. Let me show you one thing. This is very important, guys. Whenever you are gonna do PhD or something, you will be facing this a lot. So I changed my step size from 1 to 10. Initially I had a grid from 922 to 1600 with step size 1. Now I change it to 10. How it will change my code? Okay, it didn't change much. It just decreased the intensity of the points I was having. Now it looks better actually, right? It looks better. So this is what you can do. But if you change the guess, initial guess, what will happen? This is the problem, real problem. If I change initial guess, I broke the code. Okay, I broke the code here. See, this is not converging. How do I know it is not converging? Because it is giving me trash result here, 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 something like this, here and here. So we need to give a good guess, right? We need to give a good guess, and there is no answer what is a good guess. So you have to do trial and error. You have to do 20 10 10 20 15 20, all those out of combination, and run your code again and again, and then you will find a sweet spot. Okay, now it is working well. And how do you know it is working well? It is not giving you any outliers, it is giving you the physical results. Okay, it is giving you some good looking pressure versus equation of state, pressure versus energy density equation of state. So this is how you know this code is working well. And also you can also plot the residue of solver if you have an advanced understanding how numerical method work. If the residue is very small, like 10 to power minus 10, it depends upon your tolerance, then the solver is working fine. If the residue is high enough, then the solution that it is giving is not trustable. So right now it is trustable because I know I have dealt with the codes, and by looking at the curve I can anticipate, and there are no outliers here. So outliers are the point which are out of trend with the original data. Okay, now do one thing. Last thing I wanted to do is, let's change it to true. Okay, now I want to test my code with some standard parameterization. I'm gonna break my code. So when I do that, I ran it, okay, and I broke my code. Okay, for standard parameterization it is not working. Why? One reason could be I have done some mathematical mistakes while writing my code. The second mistake could be not a mistake, but I have to change this inside this thing. I have to change and play with this again and again and see where it is working well. Okay, every time I am changing it, maybe 15, maybe something else, 14, you can also do 14. Okay, so I am gonna play with that and see where I can get the solution, best solution. Now a question can come to your mind, like how do I know where to start for the guesses, right? How do you know? The simple answer to that is it should be bounded. So whatever physical solution you have, it is from 0 to 90, right? From for omega or for sigma, you can try values in between. Yeah, and you can try various combinations of them and see where it works. So some solution works for lower density, some works for middle density, some work for higher density. And if you are Python expert, like any coding expert, you can break your code, you can break your solutions, break your initial guess as per the density range, and you can find some optimization thing. For example, here you can see this guess is working fine for higher density side. These two curves are still meaningful for me, right? But it is not working well for this low part. Also it is crazy doing multiple solution for higher density part. So you can try, we can break your code in different pieces. It is your understanding how you see things, right? So right now I'm gonna do false here. I will share my code with you. and you guys have to play with it and play with the TM1 parameterization. Try as much as guess and try to do this hit and trial method and see if this works fine or not. Okay, so you can say for my default parameterization, which is not properly fitted to some properties, it is working well for the demonstration, right? And the next thing what we will do is, so this equation of state so far is in this particular state equation of state is at symmetric nuclear matter. That means number of neutrons and number of protons are same. So this particular code is not for, have I written it here? Yeah. So this particular code is for symmetric nuclear matter. This is not for neutron star matter. For neutron star matter, we have to put some additional ingredients. For example, for neutron star matter, you know that the number of neutrons are way greater than the number of protons. One thing. Second, neutron star is in beta equilibrated mode. That is one other thing. Third is the neutron star is charge neutral. Okay. So this code is not charge neutral. So we have to make it charge neutral. So that is our next thing what I am going to discuss today. But before going there, I will take a pause here and ask you if you have any questions. Okay, any question guys? If you don't have any question, just hands down. Okay, is it overwhelming or is it fine? A bit overwhelming. Okay. Okay. Okay, if you don't have any question, let me quickly go through the neutron star thing. Just a brief. You are gonna write the neutron star code yourself. I am not gonna give that to you. So I will share my IPY book, the Jupyter notebook, to you today. And using that Jupyter notebook, first you try to understand it, and then you implement some changes to that Jupyter notebook, so that we can have a neutron star code which gives us the realistic equation of state. That you are gonna do it yourself, but for that we need to go through some of the things. Okay, I will just point out something, not gonna overwhelm you with lots of things today. Yeah. So as we discussed in the previous section, we did for symmetric nuclear matter, where number of neutrons were equal to number of protons. Okay. Okay, number of protons were equal to number of neutrons, but in neutron star matter this is the case. So we need to, okay, I have already written that here. So we have Nn is equal to Np for symmetric nuclear matter, and for neutron star the matter is expected to be charge neutral, the net electric charge must vanish, and it is in beta equilibrium. What is beta equilibrium? Means that the weak interaction processes such as the beta decay must be in equilibrium. What does that mean? The rate at which neutron is converting into proton, electron and anti-neutrino, it is same as proton is converting into the opposite, right? It is back and forth thing, so that the particle chemical nature is preserved. So the Walecka model must be extended to include electrons and impose additional constraint to the physical condition. So what are the additional constraint? Why do we need electron? Because I have so far I had two things in my system in neutron star. what I had like in symmetric nuclear matter, I had number of protons, number density of proton, number density of neutron. But how can I make this charge neutral? I need to add something, right, which is electron. I can add electron, I can add muons. I am least concerned about muon for a beginning, so I will just strike it. Okay. So, the particle content I have is nucleons and leptons. And what is the beta equilibrium condition from that? Since the chemical potential should be same, so it should satisfy this beta equilibrium condition, that the chemical potential of neutron should be equal to the sum of proton chemical potential and electron chemical potential, and if muons are included, then this condition should follow. And the next important property is the total charge must vanish. That means the number of proton should be equal to the sum of number of electron plus number of muons, or if we have no muons, then it will be just number of proton is equal to number of electron, or I can say charge neutrality mean this. Okay, number of proton and number of electron, the total sum is equal to 0. It should be plus here. Okay, the total sum should be equal to 0. So, an electron will give me a negative there and they will cancel out together. Now, so for baryons we have already calculated number of protons and number of neutrons using the Walecka model, but for lepton contribution we will treat them as a free relativistic Fermi gas. That means they are not interacting. When I say non interacting, that means the effective mass is nothing but the normal mass. The mass does not change with the medium, it does not interact with the medium. So, I am treating, there is an assumption that electron mass does not change much, that is why in the same expression what I will do, I will only do for non interacting relativistic free Fermi gas. So, these are the simple expression again without the mean fields. These are the number density, this is the energy density, this is the pressure density. Okay, the rest of the thing is same. And when you do that, what additional things you have to do? You just have to add a contribution for electron and pressure of electron to the total energy density and pressure of the total system, right. So, this is what we are gonna do. So, we can extend the same code of ours so that it has like number of neutron greater than number of proton, first thing, and then we can apply a charge density, charge neutrality condition within our code somewhere, and at last we can make some corrections to the energy density and pressure, and when we have that we can construct our code. So, we can just simply modify our current code into something. Okay. Yeah, so that was my lecture so far. I feel this is overwhelming, but still we have to do it one day. So, I am opening this session for question and answers if you have any for this particular session, or if you have any queries about the previous sections or current session or assignment or anything. Okay, you have no query?
Sir, to make a CSV file, can we do with Python also, or we have to do notebook?
To make CSV file?
Yeah.
You can.
Can we do with Python also in VS Code?
Yes, you can do. I just showed you like.
Oh, that in YouTube, it was made by Python.
Yeah, it was made by Python. For example, here in this case, this is like transferring the data list, making it a data frame, and then converting it to the CSV file. So you can write CSV here, or okay, this is a CSV thing. Okay, so you can do that. Just you have to write this. This is Python pandas.
So it automatically makes it.
Yeah, it automatically makes it. You can also use Python's like pure Python functions like with, open, all those things, but they are cumbersome. Okay, one more question. Is the neutron star exercise added to assignment 2? No. Neutron star exercise is in assignment 3. Okay, so it is not in assignment 2. Assignment 2 is more about Python. So let me show you a bit about assignment 3 since you asked. See, assignment 3, it is very important to share some of the things that the part 1, which is the question I just give it to you, upgrade the current Walecka code in symmetric nuclear matter for neutron star matter. So this is you have to do. I gave you the Walecka code, I will upload it, but then you have to convert it to neutron star matter. I will be helping you, but I want you to put efforts. Okay, so you try doing it. I will give you the algorithm, at least I can do that. And then we have part 2, Beamer presentation on neutron star physics. So this is gonna be your main presentation where you guys will be presenting one by one in the last week or maybe next week. Yes, next week or next to next week. Where you will guys will give like 15 to 30 minutes talk each, where you will present everything you have learned about neutron star physics. So these are the basic ideas I have given you, that what should be inside this presentation. Okay, and I have give you some ideas, so you don't have to follow these suggestions. These are mere suggestions. One can choose their flow. I also uploaded the help files. Okay, so if you go here, notes, Rajesh presentation, you can see I have uploaded 4 or 5 files. So you just go through that. If you find some slide helpful that you can add into your slide, then do that. So do remember, your introduction should be very good, around 4 to 5 pages, so that the other people can connect with you. They don't want to get bored with your equations and everything. Anyways, we will have a dedicated session explaining all these things. For the time being, I just want to say, and part 3 is whatever change part 1, not part 1, it is part 2 now. Okay, part 2 to an article format in LaTeX, so that it is like you are submitting a report. And next, whatever you are doing, you are just upload everything in your GitHub repo, so that you exercise your GitHub skills frequently. So I will upload, I will add more. I don't think I have something to add apart from neutron star code and TOV. TOV I will provide you, just have to do some calculations. So I think that's it for today from my side. If you guys have any more questions. Do you guys need a discussion session today? Yes or no? Hands up, hands down. No? Okay, if again I am gonna repeat, if you guys are having any problem in assignment, do reach me and try to talk to yourself. If some guys are having problems, do reach other guys who you think can help you. Okay, communicate well. At the end of the internship, this is you are gonna get from that. Okay, so far so good. I think we will meet next time then. Take care.